Alright, these notes are going to be on radical expressions. Let's review a few examples of just what radicals look like. So here we have a square root of 100, here we have a square root of 49, and here we have the square root of 12. So we're going to work on simplifying these radical expressions. So 100 is called a perfect square, so the square root of 100 is equal to 10. Square root of 49 we know is also another perfect square, and that's equal to 7. And the square root of 12 is not a perfect square. So how do we simplify these? Well, if you remember, you have to look for a perfect square that is a factor of 12. And I know that 4 is a perfect square, and 4 times 3 equals 12. So since 4 is my perfect square, I'm going to take the square root of both, and I know square root of 4 is 2. And square root of 3 does not simplify, so it has to stay underneath the radical. So our answer is 2 square roots of 3. So what are some steps we can write just to simplify these radical expressions? So first, let's find the largest perfect square. That is a factor. Okay. Once we've found that largest perfect square, and it's important that it's the largest because then we know we can simplify it without taking too many steps. Then your second step is to rewrite the radicand using the perfect square we found. Okay, so just like we did up here, we found the perfect square. The largest one is 4. And that's the only one in this case, but the largest one is 4. And then we rewrote our radical by taking square root of 4 is 2. And then we left our square root of 3. Okay. Then third, I want you to check sometimes we'll think it's in simplest form, but we always have to check and make sure the other number, so in this case it was 3, has no perfect squares. What I mean by that is that that number itself is not a perfect square, and that number does not have perfect squares as a factor. Okay. Once we've checked that, and if it turns out we do have another perfect square, we just rewrite the radicand. In simplest form. So fifth step, simplify. Okay. So these are just some 5 basic steps we can use as we go through radical expressions and simplifying them. So next I want you to list all the perfect squares Up to, we'll say up to 20 squared. Okay. So for example, if I know that 2 squared is 4, then 3 squared is 9, then you have 16, 5 squared is 25, 36, 49, 64, 81, 100. 11 squared is 121. We move on to 12 squared, 144. 13 squared, 169. 14 squared, 196. And 15 squared, 225. Okay, so you should know at least up to 15 squared. Okay, we'll show you the all the way up to 20 squared. So 16 squared is 256. 17 squared is 289. 18 squared, 324. 19 squared, 361. And 20 squared is 400. Okay. So keep these in the back of your mind. You should have at least up to 225 memorized. And now let's try some examples of simplify. Okay. So first one, I'm going to write the square root of 8. I know it's not a perfect square, but let's figure out what perfect squares are a factor of 8. So I know that 4 is a perfect square, and that's a factor of 8. And 4 times 2 gives me 8. I'm going to zoom in here now that I have some room. Square root of 4 I know is equal to 2. Square root of 2 must stay underneath the radical because it does not simplify anymore. Alright, let's try another example. I have a square root of 27 this time. So my perfect square in 27 would be 9. Because I know 9 times 3 gives me 27. Here's my perfect square. Square root of 9 is 3, so that goes outside the radical. And square root of 3 cannot simplify anymore, so that must stay underneath. Alright, let's try another example, but this time, oops, we're not on number 4 yet. Number 3. This time, let's simplify a product. So this time I have a number times a radical. Okay, so 54, a perfect square that goes into 54. If I can't think right off the bat what it is, let's go through all these. So I have 4, 9, 16, 25. Let's just look at the first 4. Which one of those could be a perfect square? Well, if I look, 9 is the largest perfect square because I know 9 times 6 gives me 54. And since 9, the square root of 9 is 3, I know that will go outside my radical. Square root of 6 does not simplify, so that stays underneath the radical. But then I have this product I can't forget, so I have to bring down that product. And I have 3 times 3 outside of my radical. So I can simplify. 3 times 3 is 9. My radical of square root of 6 stays because it cannot simplify. So that is our simplified term. And as I'm going through these, so far we are working with exact answers, meaning I'm not plugging this into my calculator and coming up with an approximate decimal. Otherwise, I lose accuracy. So I want the exact answer possible. Let's try another product. 5 square roots of 24. Okay, so 24, the largest perfect square I know is 4, because 4 times 6 gives me 24. Here's my perfect square. I know square root of 4 is 2. Square root of 6, can't simplify, so that stays. I gotta bring down my product, the 5. Alright, so now I have 5 times 2 square roots of 6, which ends up being 10 square roots of 6. Alright, let's try an example with some variables. So this time, we're on example 5. Let's take the square root of 12 x squared. Okay. Alright, so we still do the same thing with our coefficient, 12. I know my square root is, perfect square is 4. And 4 times 3 gives me 12. Now, when we have variables, we have to think, how many pairs do I have here? So x squared, isn't that really just x times x? So I have one pair, which means if any pair that I have, I can take it out of my radical. So here I have 4. Square root of 4 is 2. And then I can take out that x. And I don't have any x's left over, but I do have this 3 left over, so that has to stay underneath my radical. Okay. Let's try another one with variables. So let's try the square root of 10x to the 4th times y. Alright, on this example, square root of 10 does not simplify. It's already in simplified form. But I have this x to the 4th here. So if you guys know or remember, we have x times x times x times x. That gives me 2 pairs here. Right? So that means I can take out an x squared. And what stays underneath the radical is what doesn't simplify. So 10. And y, I don't have a pair. I just have one y, so it's just 10y. So my answer is x squared times the square root of 10y. Let's try one more. So let's say we have the square root of 147, w to the 9th, x to the 5th, y times z to the 8th. Alright, let's tackle this guy. Alright, so 147, I'm trying to think of the perfect square that goes into 147. This one's a bit larger, so the largest one I can find is 49. So I'm going to write 49, because I know 49 times 3 gives me 147. Okay. Alright, so then 9, if I look at the w's to the 9th, I can write out 9 w's, or I can start thinking, well, 9 divided by 2 gives me the number of pairs I have. So I'm going to take out the square root of 49, which is 7. Okay. And I have 9 w's multiplied to each other, so that means I have 4 sets of pairs. Okay. Although I have one left over, that one left over will stay underneath the radical. So I can take w to the 4th, and as long as you can see that, you don't have to write out 9 w's every time. And then I'm going to write what should stay underneath the radical. So we know 3 should stay underneath the radical. We have a w that has to stay underneath the radical. Now let's look at x to the 5th. So again, I'm going to take 5 divided by 2 to see how many pairs I have, which I will have 2 pairs and 1 left over. So I know x has to stay inside, but I can take those 2 pairs out as x squared. Y, again, it's a loner, so it stays underneath. And z to the 8th, that's an even number that tells me exactly how many pairs I have, which are 4, so z to the 4th. Okay. All right, let's try some more examples, but this time we're going to add and subtract radical expressions. So adding and subtracting. Okay, so for this first example, I want you to write down 4 square roots of 10 plus the square root of 13 minus 9 square roots of 10. Okay, so really when we're adding and subtracting radical expressions, we need to figure out which radicals we can combine. So first check, remember I'm going to check and see if they're in simplified form. 10, yes, square root of 10, they cannot be simplified. What about 13? 13 can't be simplified anymore, so I'm going to look at my common radicals, and I'm going to combine my radicals. So I have 4 square roots of 10 minus 9 square roots of 10. So look at your coefficient. 4 minus 9 is a negative 5. So I have negative 5 square roots of 10. And I don't have any other square roots of 13, so I'm just going to write plus square root of 13. Okay, so this, you guys, is what we call an exact answer. Now, however, if I take a calculator and I type this into a calculator, and I take negative 5 times the square root of 10 plus the square root of 13, it's going to give me an approximate value. Okay, so the approximate can't spell today. Approximate value would be negative 12.2, let's just go 21. We'll round up to the hundredths. Okay, so approximate would be rounding, and we use the approximate symbol, so that's a squiggly equal sign. So approximate versus exact. Okay, so in your homework, look at what it's asking for. Is it asking for an exact answer? It has to be in this form. If it's asking for an approximate answer, it has to be in this form. Okay. All right, let's try another example here of adding and subtracting radical expressions. So I have 9 square roots of 32 plus the square root of 2. All right, so square root of 32 definitely has a perfect square. That perfect square, you guys, is 16. And I have 16 times 2 is 32. Bring down the 9, because that's our product. We can't forget our product. Square root of 16 I know is 4. And 2 has to stay underneath my radical, right? Square root of 2 doesn't simplify. Then we still have our plus square roots of 2, because we're adding. 9 times 4 is 36. So I have 36 square roots of 2 plus the square root of 32. Now remember, like we do when we think about variables, if I just have one x, that means I have a 1 as its coefficient. So here, same idea. we have a 1 in front of the square root of 2. And so 36 plus 1 means I have 37 square roots of 2. Okay, so here's another example of what our exact answer would be. And then here's an example of the approximate. So if I take my calculator again and I take the square root of 37 times the square root of 2, that's what I meant to type in. And let's go ahead round to the nearest hundredth. So approximately 52.33. Okay, so again, you guys, exact answers allow us to keep accuracy, where approximate, we end up rounding at some point in our decimal answer and we lose our accuracy. All right, so that's the difference between approximate and exact. Okay, let's try some multiplying radical examples. So multiplying, let's title this multiplying. Radicals. And I want you to use this as a rule. So if I take a square roots of c and I multiply that by b square roots of d, what I'm really looking at is I multiply the two outside terms, so a times b, and I multiply the two inside terms, c times d. And then from there we can simplify. Okay, so here's your rule for multiplying radicals. Alright, so the first example I want us to look at here is square root, let's do 2 square roots of 8 times 3 square roots of 28. Okay. Alright, so let's do the same thing. As our rule states, multiply our two outside terms, so 2 times 3 I know is 6. Multiply what's underneath the radical, 8 times 28, which we should get 224. Okay, and I can look at the largest perfect square that goes into 224. And so this is a good large number we can practice with. So square root of 224, I know isn't a perfect square. You can test it with a calculator if you'd like, but really try to write out your factors. 16 is the largest one I can find for a perfect square, and so 16 times 14 gives me 224. So here's my perfect square, which is the 16. And then we simplify. Okay, so now we bring down our product, the 6, and then we take times 16, or sorry, not 16, square root of 16, which is 4. And we leave the square root of 14 underneath. And my final answer would be 24 square roots of 14. All right, let's try one where we have to distribute a radical. So if I take the square root of 2 and I'm multiplying that by the square root of 2 plus 3 square roots of 5. Alright, so let's distribute. Now remember that when I am multiplying a radical with the same number, the radical will go away, and this is why. So 2 times 2 I know is 4. What's the square root of 4? Square root of 4 is 2. Alright, this will happen for any value. If I have the square root of x times the square root of x, my answer will be x. Okay. All right, and then we have plus 3. Now we have to multiply what's underneath the radicals. 2 times 5. And so I have 2 plus 3 square roots of 10. And we know 10 doesn't simplify, so here's our exact answer. Okay. And what would be our approximate answer for this? If I take my calculator and I type in 2 times the square root, or 2 times 3 square roots of 10. So let me show you what I'm typing. 2 plus 3 square roots of 10. And I end up with 11.49. Or approximately, this would be our approximate answer. Okay. All right, let's try one where we have to FOIL. Do you guys remember how to FOIL? Now this will be a good review on FOILing, which is really distributing our terms, but FOIL is our acronym we use. So first side is 7 times, or 7, square root of 7 times the square root of 7, which I know, like we mentioned up here earlier, same value, same square root, the square root goes away. Okay. Then times our outside term. So I have minus 3 square roots of 14. Then our inside terms plus square root of 14. And then our last. So square root of 2 times a negative 3 square root of 2. So I have negative 3 times 2, because our square root goes away. Alright, so I have 7 minus, combine my like terms, 2 square roots of 14, and then minus 6. Okay, and then I can combine my constants. 7 minus 6 is 1. And then I'm left with minus 2 square roots of 14. All right, dividing radicals. So let's show the steps on dividing radicals. Okay. So our general rule for dividing radicals will be to write it this way. So if I have a ratio or a fraction underneath a radical, right? So if I did a divided by b and took the square root, it's the same thing as taking the square root of a over the square root of b. Okay. So let's use this as just a general rule we can look back to. So let's do some basic examples. If I took the square root of 2 over 25, I'm going to break apart that radical and rewrite it as the square root of 2 divided by the square root of 25. And I know square root of 2 doesn't simplify, but square root of 25 is 5. So here's my answer, square root of 2 over 5. And I leave it in that simplified form. Unless you're asked for approximate, you'll have to find the approximate value. All right, let's try this one. We have square root of 4x squared divided by 81y squared. Okay. So again, I want to break apart my radical. So square root of 4x squared divided by the square root of 81 y squared. And I know that I have a bunch of perfect squares here. So square root of 4 is 2, square root of x squared is x, square root of 81 is 9, and square root of y squared is y. Okay. Now what happens if, I'm gonna need some more paper here. What happens if I have something that looks like this? So we started with the square root of 2 over 25. What happens if I have the square root of 25 over 2? Okay, so if I keep looking or keep working it, I take square root of 25 over square root of 2. But square root of 25 I know is 5, and square root of 2 is in my denominator, but this is a red flag. We can't have a square root in the denominator. That is a math rule. So we cannot leave a radical in the denominator. So how do I get rid of it? Well, to get rid of that radical, you have to multiply by rationalizing. So we call this rationalizing the denominator. What I'm going to do is I'm going to take that square root of 2 and turn it into a fraction of 1. So square root of 2 divided by square root of 2. I call this a fancy one because it has a radical, and square root of 2 over square root of 2 just equals 1. So I'm not changing the value of my radical, but I'm getting rid of that square root that's in the denominator. Okay, so then I'm left with 5 square roots of 2, and we know the square root of 2 times the square root of 2 equals 2. So now I have all my bases covered. It's in simplified form. And we call this rationalizing the denominator. Okay. All right, let's look at another example where I have the square root of 9 over 8, and I break apart, rewrite it square root of 9 over square root of 8. The nice thing here is that 9 is a perfect square. So I have 3 over the square root of 8. There's my red flag. There's my square root in the denominator. Gotta multiply it out with the fancy one. So I'm going to take the square root of 8 over the square root of 8. And then I'm left with 3 square roots of 8 over 8. And notice it's not in simplified form yet because the square root of 8 has a perfect square as a factor. And we know that is 4. And 4 times 2 is 8, so I have 3 times 2 square roots of 2 over 8. Okay, and 3 times 2 is 6, so I have 6 square roots of 2 over 8. And you guys, can we look at the square root of 8, or not square root of 8, 6 square roots of 2 over 8. Can we still simplify that And we can, because 6 over 8 reduces to 3 over 4. So 3, oops, not 4, 2. 3 square roots of 2 over 4. Okay. Now let's try one more example where I have 10 divided by the square root of 5. Right away you should say, oh no, that's not right. Can't have that square root in the denominator. Multiply by that fancy 1. And I have 10 square roots of 5 over 5, and I can reduce, because look, 10 divided by 5 is 2, so my final answer is 2 square roots of 5. All right, let's talk about conjugates for a second. So we need to know what conjugates look like. So here are some examples. If I start with this square root of 5 plus 3, my conjugate is going to be the same square root of 5, the same 3, but what changes is the minus. So whatever I have, if I have a plus or if I have a minus, the conjugate will change the sign. So what if I have, for another example, square root of 3 plus the square root of 5. My conjugate would be square root of 3 minus the square root of 5. Or, what if I have the square root of 2 minus 1? My conjugate would be square root of 2 plus 1. So again, we're changing only the side that's between the two numbers. So if we're subtracting, then we're adding. Okay. Why do we need conjugates? So let's take this example that we just did and multiply. So try multiplying them. So square root of 2 minus 1 times the square root of 2 plus 1. Alright, so now let's take square root of 2 times square root of 2. We know is 2. Square root of 2 times 1, positive square root of 2. Square root of 2 minus times the negative 1 is minus square root of 2. And negative 1 times 1 is a negative 1. Okay, well notice what happens. These equal 0, right? Square root of 2 minus square root of 2 is 0. And I'm left with 2 minus 1, which is equal to 1. So my square roots go away. My complex square root of 2 minus 1 now becomes 1 when I multiply it by the conjugate. This is so helpful when we multiply by a conjugate and we have a square root in our denominator. So let's try an example of what we would use a conjugate for. So if I have 1 divided by the square root of 3 plus 2, and I say simplify this. Well, how do I get rid of that square root? I have to use a conjugate. Okay. Now the conjugate again will be turned into a fancy 1. So I'm going to take the square root of 3 minus 2. Square root of 3 minus 2. Still have to make it a fancy 1 so we don't change the value of our expression and our number. So we have square root of 3 minus 2 in my numerator. And then let's multiply to figure out what our denominator will be. So square root of 3 times square root of 3, you know, is 3. Square root of 3 times negative 2 is negative 2 square roots of 3. And then this is where you should see that these will cancel out to 0. So plus 2 square roots of 3. And then minus 4. Alright, so let's finalize our answer. We have square root of 3 minus 2, all divided by, now let's combine our like terms. These we know equals 0. 3 minus 4 is negative 1. And that negative 1 we don't need to keep in our denominator, but we take that negative out front and make negative 3 square root of 3 minus 2. And that's it.